Hello guys, in today's lesson in physics, we're going to be discussing two-dimensional motion. In our previous lessons, we discussed one-dimensional motion. We carried out a couple of lessons on one-dimensional motion. We discussed how bodies could move along either the x-axis or the y-axis. When bodies move along the x-axis, we call it acceleration of bodies from rest. While when body moves along the y-axis, we call it acceleration due to the effect of gravity. You see that the body will be rising or the body will be falling. But today we're going to be looking at how a body could move in both dimensions at the same time. Our body could move either along the x-axis or along the y-axis simultaneously. So today we're going to be looking at a couple of things that will help us achieve this kind of motion. So when we talk about two-dimensional motion, we're talking about, okay, let's say for example, the velocity of a given body, either velocity of a given body, acceleration of a given body, or probably could be, it could be force also. So the fact is, either of those vector quantities that have been mentioned experience two component sort of movement. For example, let's say velocity. Let's say the velocity of a body. Let's say a body moves like this. Let's say a body moves like this. For example, this is the resultant speed. We're going to be discussing this, in the next couple of lessons. The body moves this way, for example. So the fact is, if the body moves this way, I mean the body is going to be covering, two kinds of motion. Now we also call two-dimensional motion. We also call it angular motion. Now it's not only two-dimensional motion that we have. We also have a three-dimensional motion. We also have four-dimensional motion. We're going to be staying focused on two-dimensional motion. So we also call them either two-dimensional or three-dimensional. We call them angular motion. So if a body moves with this kind of velocity, it means the body experiences two kinds of component. The body moves along x-axis and along y-axis, positive x and positive y-axis. This is what we have. The body moves along x and along y. Let's say, at this angle with the horizontal. So this is the resultant of the movement. This is a vector quantity, this velocity, why it takes place in two dimensions along y and along x. So you can have a unit vector I here, a unit vector j. So this is a two-dimensional motion. So we talk about the result of this, the total, velocity. We talk about something like this, the sum of the whole velocity that is along, the x-axis and along the y-axis. So this is a perfect example on two-dimensional, motion of bodies. So what are the major, things that bring about two-dimensional motion? So we're going to be looking at them. There are a couple of things that we're going to be discussing under two-dimensional motion. The first we're going to be discussing is projectile. Projectile is a very good example. Projectile is a perfect example to exemplify two-dimensional motion. So the next we're going to be discussing, we talk about circular motion. Circular motion, particles of body experiencing circular motion. And also we're going to discuss, SHM, simple harmonic motion. It's another very good one, simple harmonic motion. We're also going to discuss what we call the related motion. So all these sort of motions are perfect avenues to explain what we call the two-dimensional motion. But for today, we're going to be discussing projectile. And don't forget, two-dimensional motion is an angular kind of motion. So just like the three-dimensional motions, for example, a person swimming in the pool, the person can go right, can go left, can also go the depth of the pool, even an airplane. And other kinds of examples like that. Four-dimensional motion is also there. So, but today we're discussing two-dimensional motion, and we're going to be starting with projectile. Okay, guys, you're going to be starting with projectile. Now, there's a right way to pronounce it. Projectile. Projectile. So when we talk about projectile is one of the major avenues to really discuss the two-dimensional motion, a sort of angular motion. So we're talking about projectile, we're talking about a given body that does this. Just look at what projectile is all about. So when you talk about projectile, a body is being projected at an angle to the horizontal, for example, either horizontal or vertical, but mainly horizontal. So the body does this, it gets the maximum height, as we discussed in our previous lesson, then the body then returns. Now, one very thing I want to know, this body itself is what we call projectile. It may be an object, it may be a ball, it may be anything. We're going to be looking at examples of projectile. So the body leaves at an angle. Now, the reason why we call this two-dimensional motion or angular motion is simply this. This very body is not just projected upward. It's not thrown upward or thrown horizontally, but the body is thrown at an angle, just like this, or more or less like a shot put or a javelin, So the body is thrown at an angle. So when the body is thrown at an angle, the body does two things. It gets to max height first, and when it gets to max height, it starts falling back. So a couple of things happen under projectile. First, the body is being projected with an initial, velocity, a kind of initial force, sends the body into motion. Now, provided there is, also most times there's always air friction, but most times it's often negligible. So the body gets into the air. So then it starts dropping back after it gets to maximum height. At maximum height, it loses all its initial speed. So the body from here falls back to where it's been thrown from, falls back to the ground. So two things happen. There's an initial speed that takes the body into the air, into flight. So there's also a speed, a kind of force, gravitational force, that sends us back to the earth. There are a couple of things we have to know when it comes to the derivation of the formulas to solve projectile. Now, today you're not going to be solving questions. You're just going to be deriving all the formulas we're going to be, using to solve different questions. So before we go into this, there are certain things you have to know. Now, don't forget, in our previous lesson, we worked on one-dimensional motion. So you have to go back and revise that very lesson. We're going to be needing equations of motion, things like this, v equal to u plus at. We're going to be needing this to derive all our formulas. We're also going to need s equal to v plus u over 2 times time. We're going to need, this v squared equal to u squared plus 2as. Just writing them out randomly. We're also going to need s equal to ut plus half at squared. And also, that's my favorite one, dt is not very common, minus half at squared. So if you've not gone through the previous lesson, you have to go ahead and learn these things, because they'll help you. And also, you're also going to need the knowledge of trigonometry ratio. You understand? Knowledge of something like this. SOHCAHTOA, for example. SOHCAHTOA is very important. Don't forget SOHCAHTOA. Sine is opposite of hypotenuse. Cosine is adjacent of hypotenuse. Tangent is opposite of adjacent. And stuff like trig identities, S sine A plus B will give us sine A cos B in bracket plus cos A sine B. So for you to understand what we're about to take, you need the knowledge of this, the equations of motion that were treated in the previous lessons, and also our trig function. Okay, right now we're going to be discussing the various terminologies under our projectile. So yeah, the various terminologies. So look at them. These are the terms we use under our projectile. The first term we have is what we call the total time of flight, or just call it time of flight. The next term we have is what we call the max height, maximum height. The max height, you just write. The max height is the next we have. After the max height, the next we have is the range. The range is the horizontal distance between a point where a body was projected from to where the body hits the ground. So the next we have either the ground or any other place. So the next we have is the landing velocity. We have the landing velocity. And the very last one we have is the trajectory, which is the parabolic path. Trajectory, known as the parabolic path traveled by a given projectile. And don't forget, a projectile is simply a body, is an object that travels through a parabolic path, through a curved path, this curved path here, after it has been impacted upon by an initial, velocity at a given angle. So the body travels through this curved path, and gravity acts on the body. First of all, the body gets to maximum height before gravity sends it back to the earth or back to any other place you want to send it to. So that's what a projectile is. So we have different examples of projectile. We have the various examples. For example, a catapult is a perfect example. Missiles. You wonder how countries hit other countries with rockets and missiles. It's through the help of projectile. That's part of science. Very important. Missiles, rockets, shot put, under spot, javelin, and so on and so forth. All these are examples of projectile. When you take an object, a catapult, for example, and you project it at an angle, it does two things. It gets to maximum height, the object, the projectile. It could be a stone, it could be anything. gets a given max height before gravity then starts sending it back. But two things happen. As the body moves, the body covers a distance on the horizontal axis and also a distance along the y-axis. And that's how I call it two-dimensional motion. The body covers a distance along the x-axis horizontal, also a distance along the y-axis. So the body moves in two direction or dimension simultaneously. So we're going to be starting with the total time of flight. Okay, when we talk about time of flight, what does time of flight simply mean? Now, it's very simple when we talk about time of flight. Now, imagine a body is being projected from this place. Let's say a javelin. Somebody takes a javelin and throws it like this. Now, something happens. The body goes up like a javelin. Let's say a javelin thrower, for example, or a hammer thrower. So the body it goes this way. Now, it gets a certain max height because it cannot keep going forever. Now, as it's going up, it's covering distance along x and also distance along y. Somebody projecting the javelin like this. So it gets a max height. At max height, it cannot go beyond this level. That's the first phase. So the phase one is the phase of max height. That's it here, the phase of maximum height, whereby the body is not going to go beyond that level. It loses all its initial velocity along the y-axis. So at this very point in time, the body starts falling. Gravity now takes over and sends it back to the ground. So you see a body is being thrown from here. The body goes like this and hits this region. So that's that. So when we talk about time of flight, you have time of flight, two type of time of flight. At the time of flight, it takes the body to get to maximum height. And the time of flight, it takes the body to move from that maximum height back to the ground. Now, provided there is no air friction, provided there is no wind or there's no air friction, for example, it means it's going to take it the same exact time of flight, the same exact time I need to get the maximum height. It's going to take that same time to fall back. So if you take it 2 seconds to get to the max height, it's going to take it another 2 seconds to fall back. So the time of flight is simply the time it takes a given projectile, which is a body, to get to the max height, and also the time it takes that same body to fall back to the ground or to the earth. So let's look at it. Don't forget, we're going to be needing the knowledge of, SOHCAHTOA, very important. So this is initial speed. Yeah, so for the fact that the body is being shot with this velocity, it means it's going to move in 2 dimensions. That's what I call it, two-dimensional motion. So at initial speed, so the body does this against the horizontal theta. So the body is going to cover 2 dimensions, one along y-axis and one along x-axis. Now don't forget SOHCAHTOA. Opposite, hypotenuse, adjacent, very important. So uy over u, opposite by hypotenuse, is sine theta. So uy is u sine theta. So the initial velocity of the body along y-axis is u sine theta. So let's see that for along the x-axis. So ux over opposite hypotenuse adjacent. So adjacent over hypotenuse equal to cos theta. So we cross multiply. Ux is u cos theta. So this is the initial velocity of the body along the x-axis. So that means immediately the body was projected, it experiences 2 kinds of initial speed. So the body moves along y-axis, y rising, and also moves along x-axis on the horizontal. It's very simple and practicable. So what do you have here? This u sine theta, this u cos theta. So after I've gotten this, the first thing we're going to get is you're going to get the time it takes the body to get to maximum height. So don't forget the equations of motion. Let's try out. We have v equals to u plus at. So now let's try. Don't forget that the body did not move on the ground. The body did not move on the floor. All the movement took place in the air. So it got to max height, it gets max height, I beg your pardon, and falls back to the ground. So this is what happens here. If we use this, v equal to u plus at, it's going to be along y-axis. So that will be vy equals to uy plus ay times time. Time doesn't have a business with y or x. Time is a scalar quantity. So now at max height, first of all, at max height, you know that from our previous lesson, that at max height, final velocity for the body along y-axis is 0 meter per second. So at max height is 0 meter per second. Initial velocity is u sine theta. So at max height is 0 meter per second. Initial speed is u sine theta. Then acceleration, don't forget that when the body rises against gravity, acceleration due to gravity is negative gravity. So that will be minus gravity times time. This is time for max, T max. So what do we have? We send this to the other side. That's gt equals to u sine theta. So the variable side by gravity, we also get the time max. So the time max, T max, is u sine theta over gravity. That's what the T max is. So there's the time it takes to get to the maximum height. The time it takes to get to the maximum height is simply this. So now let us see the time it's going to take, to complete the whole journey. If it takes this to get to the maximum height, don't forget it's in two phases. The first phase is the phase where it's going to get to maximum height. The second phase is the phase whereby gravity kicks in and sends it back to the ground. So it gets to the maximum height using this. So gravity sends it back to the earth. You understand? So that's the second phase. Now, for the fact that there is no air friction, if there is no air viscosity or air friction, the rule is this: the time it takes it to get the maximum height is the same time it's going to take it to fall back to the earth. So the total time of flight, total time of flight, total time of flight is 2 times T max, time it takes it to get the maximum height. The total time of flight is 2u sine theta over gravity. I'll use the capital letter T, uppercase letter T, and me to explain that. So that's that for time of flight. Don't forget there's a time it takes a body to do two things. First of all, to get to max height, and also to fall back to the ground. Okay, guys, the next term we're going to be talking about is max height or maximum height. And we just finished the time of flight. So we'll talk about the max height of a given projectile. Now, what does it mean? What does it mean for a body to get to max height? Don't forget, the max height is simply the height attained by a given projectile or a given body. Projectile is known as an object. You understand? So the time it takes, the height, I beg your pardon, it takes the height a body or a given projectile attains, whereby the final speed along the y-axis of that given body is zero. That's what we call max height. So at max height, don't forget, the body is going to leave with a given initial speed of velocity. And it's going to do that at an angle. It's not leaving vertically. It's not like the object is thrown up or the object is thrown in this direction. But the object is thrown at an angle, just like this, at an angle to a given horizontal. So that's why we call it angular. So for the fact that the body is thrown at an angle, it causes the body to go in two dimensions. The body goes this way, is going along the x-axis and also traveling, rising along the y-axis. So as it rises, it gets to a given height, whereby it loses all the initial speed along the y-axis with which it leaves with. So at that very point in time, whereby it loses everything, gravity sets in and sends it back. So it's more or less like the initial speed acts against gravity first, disrespecting gravity, let me say that. Before it loses everything, then gravity sends it back to the earth. So the max height is simply that height whereby the body, whereby the final velocity of the body is zero. Is that height whereby the body loses all its initial speed, before it's being sent back to the earth. That's a maximum height. So what equation of motion are we going to use? Don't forget, we are still working on that kinematics. This is kinematics. You're not considering forces mainly here. So now let's look at equation of motion. Which of them is going to be the best for us to use? Now we have v equal to u plus at. You're not going to use that. That's not the best. If we have you're looking for mass height. If you have s equal to ut plus half at squared, this is another one, but you don't have time. We're not talking about time here really. If you have v squared equal to u squared plus 2as, s equal to v plus u over 2 times time. So we're not talking about time really. So let's use this. This does not have time. So we have final velocity at mass height is going to be zero. Initial velocity, we know what it is for along y-axis. Everything we're talking about here is along the y-axis. The body is not moving on the ground. The body, the mass of the movement, the mass of the movement takes place in the air. You understand what I'm saying? So what do we do? So we're going to be using this. We're going to be using v along y-axis. This is equal to u squared plus 2 along y-axis. Then don't forget, distance along y-axis is known as height. So this height, the maximum height we are discussing. So don't forget the initial speed along y-axis. According to analysis, the body comes out like this, moves in two dimensions. Opposite hypotenuse, initial speed is u sine theta. That's the initial speed, and is well known. So the final velocity at max height is 0 meter per second, and that's why it is maximum height. It's a height whereby a body cannot go beyond because it has lost all the speed with which it leaves the kind of speed, so it has lost all the initial speed. It's left the very point of projection with. So this Vy is final velocity at max height is 0 meter per second. Acceleration is minus gravity because the body moves against gravity. The body was rising. So the distance along the y-axis is written as height, h max, and we call that h max. So it's high time we fixed all this into what we have. So the final velocity is 0 squared. Initial speed is u sine theta raised to power 2 plus 2 times minus gravity times h max, the max height. So what do we do next? The next thing is this, the 0 equals to, let's say u squared sine squared theta. Don't forget, trig identity, trig function, very important. So what do we have? Minus 2gh max. So what do we do next? We send this to the other side. So 2gh max equal to u squared sine squared theta. So we're looking for the maximum height, formula for maximum height. So you divide both sides by 2g, both sides by 2g. So the formula for the max height attained by the body is u squared sine squared theta over 2 times gravity. So the maximum height can only be gotten when the body gets to when the final velocity is 0. That's the maximum height. So this is the formula. To get the maximum height of a given projectile is initial velocity, at no dimension, you can see that, squared times sine squared of the angle over 2 times the gravity. As simple as that. Okay, it's time to look at the next one, which is a third and terminology. It's called the range. So when we talk about the range, what does the range mean? Even from the name, range. Range is simply, a kind of gap between two major positions. The space, the gap between two major positions. So when we talk about range, we are talking about, now look at a body is being projected from this place. That body gets to maximum height, which is the first phase, then returns to the ground or to the earth. Now don't forget, it's not really returning to that very spot it was projected from, but on the still on the same level ground, on the same ground. So range is simply the distance from here, from where the body was projected, to where the body lands. That's what we call range. So for example, somebody who throws a javelin. So you throw the javelin at this very spot. So it goes right into the air. Then gravity sends it back from our side. Then it hits another spot, probably on the same horizontal ground, likely, very likely. So that's what we call the range. So when we talk about range, it's simply the distance between the point of projection to the point of landing, to where the body lands. So the distance on the straight line along the x-axis. Here for range, we are talking about everything we're talking about is along the x-axis. Don't forget the past two terms we talked about were along the y-axis, the time of flight and the max height. So, but this time around, we're talking about stuff along the x-axis. So let's say how we get the range. So it's very simple. Don't forget initial speed along the x-axis that we got as u cos theta, initial speed along the x-axis. Now, for the fact that this body is not moving on the ground, the body is not moving on the ground, on the earth. The body moves in the air, you understand? Although the body covers the distance along the x-axis, but there's no movement actually on the ground. So the fact is this, for the fact that there's no movement on the ground, it means there can be a change in velocity on the ground, along the x-axis, I mean. So for the fact that there can be a change in velocity along the x-axis because the body does not move on the ground, it means the final velocity is the same thing as the initial velocity. That's just a rule. So now we are looking for the range. The range is horizontal distance from the point of projection to the point of landing. So how do we get the horizontal distance? We are looking for this horizontal distance. This is what we are looking for. So we have almost have all our parameters, and we have acceleration. There's no acceleration along the x-axis. Acceleration is 0 because the body has no movement on the ground, and that's why initial is got to final. So we are looking at let's look for the best formula we could use among the equations of motion. If we use this, initial this, we have time. The time we are talking about here. One major thing is this: for range, this rule is still applicable. The body gets the max height first, before then it returns. So two things happen. The time is going to take it to max height. It's the same time it's going to take it to fall to this very position for us to now get the range from here to here. So we're going to be looking at range in two dimensions, in two ways. First of all, the halfway range, which is a range it takes the body, which is a range for time to get to max height, and therefore get the complete range, which is for the total time of flight. So don't forget range is simply the distance between here and that very place. So now let's see what we're going to use. We could use this. Let's try this out. S equals to ut plus half at squared along x-axis, acceleration along x-axis. Time doesn't have a business with x or y because it's a scalar quantity. So we are looking for this is the range x. So we are looking for, so what's the initial velocity along the x-axis is u cos theta. Now the time you're going to be using, don't forget the time of flight. We're going to be using, normally, don't forget the time we got. What did we get as our time? When we got our time, don't forget what we got in our time. When we got the time first. When we got the 0, u sine theta gt. So we got the time for max height. We got the time for max height to be u sine theta over gravity. That's what we got the time for max height as. And also we got the total time. Total time, absolute time is 2u sine theta over gravity. So we are going to be using the absolute time. That's what we're going to be using. So we could use this if we want to, but there's the right thing to use. You understand? So now we are going to use the time it takes the body to get the max height and also fall back. So the total time of flight is 2u sine theta over gravity. That's the total time of flight. Now, plus, now what do we have here? Acceleration along x-axis is 0 because the body does not move on the ground. So all this are gone. So 0 plus nothing. 1 over 2 times acceleration along x-axis, I beg your pardon, then times the time, total time. So everything is going to be wiped out. So these are the things you're going to be working with. S equal to u cos theta in bracket times 2u sine theta over g, all in bracket also. So the side time we multiplied this. The distance along x-axis, as a range that we're talking about here, r, is what do we have here? So we have 2u squared, then times sine theta cos theta over 1 times g is gravity word, gravity. This is where trig identity comes in to help us. And that's why I said at the beginning of the lesson that you should have the knowledge of trig identity. If not, you may find yourself lost at this very junction. I'm going to try my best to help you stay, connected. So 2u squared times sine theta cos theta over gravity. So how do we solve this? Now, don't forget, there's a rule for trig function, for trig identities. We wrote it the other time, sine a plus b. We give us sine a cos b plus cos a sine b. This is what we're going to get. Sine a cos b is equal to sine over bracket a plus b is equal to sine a cos b plus cos a sine b. Now let's assume that the a and b are the same. Let's say a is equal to b. So if a is equal to b, so let's say they are both tan theta. Say sine theta. So that'll be sine 2 theta. If a is equal to b, if the angle a and angle b are the same thing, so it's going to be let's say a is theta and b is theta. So them are both theta. So that'll be sine theta plus theta, that's sine 2 theta. So what's that going to give to us? I'll give us sine theta cos theta, then plus cos theta sine theta. So what do we have there? What we're going to have there is sine 2 theta equals to sine theta cos theta plus cos theta sine theta will give us, they are the same thing, will give us 2 sine theta cos theta. We are trying to work on this very stuff. So sine 2 theta equal to 2 sine theta cos theta. And what we are looking for is sine theta cos theta. So what do we do from there? We divide both sides by 2. So it means sine theta cos theta is equals to sine 2 theta over 2. That's what it is. So now we're going to take this and put it into this place. So we're almost there. We take this and put it here. So what do we have? The next thing we have is this. Don't forget we are still working on range. I've almost gotten the formula for range. We've gotten the formula for range. So what do we have? The range now is going to be 2u squared times sine theta cos theta is equal to sine 2 theta over 2. Sine 2 theta over 2 all over, what do we have? Gravity. So 2 year 1, 2 year 1. So the range, this one along x-axis, is u squared sine 2 theta over gravity. This is a perfect formula for range. This is how to get, this is a formula for range. So if you want to solve for range, all we just have to do is, they'll give you the angle, so it's simple, initial speed. So there's a perfect formula, square of the initial speed times sine 2 times the angle over gravity. And that's why there's a max angle. The max angle of projection is always 45 degrees for range. So it's u squared sine 2 times 45, which is sine 90 over gravity. So the range is going to just be u squared times 1 over gravity. So the mass angle of projection is always half of the 90 degrees, half of the perpendicular angle, I beg your pardon. So this is a formula for range, as simple as ABC. Don't forget, for you to prove this, you need the knowledge of three identities. Okay, guys, let's look at the penultimate terminology for projectile. So what we have here is landing velocity. Now, landing velocity. Now, when we talk about landing velocity, you're talking about the velocity, you know, with which a given projectile or body hits a given target with. So the fact is, when a body is being projected at a given angle, when a body is also known as a projectile. When a projectile is being, sent out at a given angle, it could be a missile, it could be a rocket, it could be whatever it is. When it's being sent out, there's always a target. So now the speed with which it's going to impact that very target with is what we call the landing velocity. So landing velocity is the velocity of impact. So it depends. For landing velocity, it depends on a whole lot of things. It depends on, let's see what it depends on. Let's look at two scenarios. Let's say on a level ground, let's say on a level field, a body is being projected. Let's say a javelin. I love javelin a lot. Very good example. A javelin is being projected. The javelin gets a maximum height, then falls back to this. Let's say there's a target. It hits this target like this. It could also be, it could be anything. Let's say javelin actually. So now don't forget the javelin leaves at this very angle of projection, like this. It leaves like this, it goes, get to max height, which is the first phase, then falls back to this place. Now it's going to leave with a given initial speed. Now don't forget, as you can see, the heights involved there are the same height. The body leaves, get to max height, and that's at max height, then it falls back to this place. So at maximum height, this max height here. So we now look at, now gravity takes over from here, sends us back. Now, from here back to this place is still the same maximum height. So nothing changes. So first it moves from here to here, max height, then sends it back. So for the fact that there's no air friction, for example, and everything is intact, no air friction, so we can assume that this, when we look at this, the speed with which the body will impact the ground with, you understand, the javelin, now it's going to impact the ground with this velocity, this final velocity, this initial. So the component is going to be in two ways, in two angles. So there's it here at an angle theta to the horizontal. So it impacts the ground with this final velocity, velocity along y, and velocity along x axis. Now the resultant landing velocity, you understand, is going to be the same thing as the initial word velocity with which the body leaves with. You understand what I'm saying? It's going to be the same thing. Why? Because it's the same height. The body gets to this place, and then so the same height involved is involved. I mean, but if I have something like this, let's say the body is projected, and there's a building some meters away. The body goes like this. Now this is different from this. Now don't forget, the body is going to go like this. It could be at max height. If you look at the height, it takes to get to, let's say there's a maximum height actually. You know, the speed with which it takes the body to get to mass height, it's not the same speed it's going to take the body to start falling back. So let's say there's a mass height here, for example. Let's say let's assume that the mass height was somewhere around here, and the body is on its way back to the ground. You understand? So around here is the mass height. So from here going back to the earth, it landed on the building. So you can compare the distance from here to max height and the distance from here to the top of this building. So the impact velocity will be quite different. You understand what I'm saying? So there are certain things you have to know. For this, for landing velocity, the final velocity along the x-axis is the same thing as the final velocity along initial velocity, I beg your pardon, along the x-axis. They are the same thing because the body does not move on the ground. So yeah, don't forget initial speed along x, same as final speed along x. You understand? For landing velocity. Why? Because the object does not move on the ground. Now, for the initial speed along the y-axis may not, it's quite conditional, it's contingent on if the heights are the same. The initial velocity along the y-axis is going to be the same thing as the initial velocity along as the final velocity along the y-axis, provided we have a constant height. Provided the height we have are constant. It gets to this max height and falls back. You understand? So, but the only difference is that's going to be negative. look at initial speed going up to the mass height. Now the final velocity coming back as falling back to the ground like this. As you can see the direction. So this is going to be the same thing with what we have here. Initial speed along y, initial speed along x. So it's going up like this while it's coming down like this. So they'll be the same thing but with different directions. So this is going to remind us, provided the height involved, we have the same height. The body rises to this place max height and it's coming back to impact this position. So they're going to be the same thing provided that we have the same height. But for this, it's not going to be the same thing. Initial speed along s is the same thing as final speed along x. This is constant. Why? Because we have there's no acceleration on the ground. That's the reason. But for this one, the final speed along y cannot be the same thing as the initial speed along y because of it's not the same height. The height covered to get to maximum height is not the same height when the body starts falling back under the effect of gravity. A building was standing in its way, like this. So now let's derive what we're going to get. What I'm going to get. Let's look at this. This is the final velocity. So you have something like this. So against the horizontal. So what are we going to have? This is a resolution. This is what we have. Final velocity here along x. Final velocity along y. That's what we have. So now let's analyze it. Opposite over hypotenuse. So Vy over V equals to, what do we have? Sine theta. What's same thing with this? So Vy is V sine theta. So if Vy is V sine theta, then Vx is final velocity cos theta. So how do we get the resultant? How do we get the resultant? We're going to use SOHCAHTOA. We're going to use Pythagoras theorem, I beg your pardon. So V squared equals to U squared. V squared equal to, Vy squared plus Vs squared. So the final velocity is square root of Vy squared plus Vs squared. This is a resultant. Now, if the heights are the same, don't forget the heights are the same, the Vy will be minus Vy. But doesn't mean, because you're talking about the square of it. So this is the resultant landing velocity. This is the landing velocity for this very given body. So we can also get the angle, the landing angle, opposite hypotenuse adjacent. So the landing angle opposite over adjacent, Vy over Vx equals to tan theta. So what do we have? The angle of landing. This angle of landing is tan inverse of Vy over Vx. There's the angle of landing, as simple as ABC. This is a landing angle. So this is the landing velocity. This is the landing angle. Okay, guys, it's time to look at the last terminology on projectile. So right here, we're going to be discussing what we call the trajectory. So when we talk about trajectory is simply the path, the parabolic path taken by a given projectile. So we have something like this. So this body is being projected like this. So this parabolic path, we're talking about parabola, we're talking about the curved path. This curved path taken by a given projectile is what we call trajectory. This is a trajectory. So the beautiful part of trajectory is this. Trajectory helps us to know the position for a given projectile at every time instant. You understand? So when we talk about trajectory, when we get the formula of trajectory, it will help us to know where a given projectile is. It will help us to get to know where a given projectile is either at max height or not at max height. For long, we've always been talking about maximum height. This maximum height here. This max height. So we could easily get to know the position of a given body along the y-axis. That is the distance of a given body along the y-axis at this max height. But when it comes to trajectory, we don't really even need max height. All we just need to do is we just need a formula that can help us, help us to bridge, or that can help to show the relationship between the y-axis and the x-axis. So what trajectory does is that it helps us to know the position of a given body at every given time instant. At max height, even when it's not a max height, at this position, at any position, during the whole movement. So for the trajectory, we're going to be this trajectory here, the curved path. This curved path is trajectory. We call it trajectory, the parabolic path. So now for the trajectory, this here, we're going to be looking at distance along x and distance along y axis. We're going to be fusing them. But the time you're going to be using, since you're not using max height. You're not going to stay focused on max height. It means you cannot use the time at max height. So the best time you're going to use is the time along the x-axis. Don't forget, I want to talk about time. You're not really, time doesn't have a business with x and y, but at this very point in time, I'll love us to stay focused. I'll love us to see in a different light, in a different way. So the time you're going to be using here should be time along the time along the x-axis. You're going to see what I'm talking about. So don't forget the equation of motion. V equal to u plus at, very important. Then s is v plus u over 2 times time. You're going to be needing a couple of them to prove this. Then we have b squared equal to u squared plus 2as. S is ut plus half at squared. And s also could be bt minus half at squared. So now we're going to be getting the time of the body at along the x-axis. Now we are not using time at mass height because we are not restricted. For mass height, there's a restriction. That's with mass height. For mass height, final velocity is 0. But this one is velocity or the position of the body at any given time. It could be at mass height, it could be at beyond mass height or before mass height. That's what trajectory is all about. To help us to get the position of every given projectile at every given time instant. So what are we going to do? Let's get the time first along x-axis. Let's try this out. V equals to u plus at. Now don't forget, here, we can't even use this. The reason why we can't use it is that the final velocity and initial velocity are the same. So there's no need to use this. I beg your pardon. Just let's see what we can use. We can use this, and also we could also use this to use this and this. Let's just use this. So S is V plus U over 2 times time. Don't forget, along x-axis. Along the x-axis, the final velocity is written as initial velocity along the x-axis. Why? Because there is no movement on the ground. All the movement merely is in the air. So we're trying to get time for movement along the x-axis. That's the best thing we can use. We can use for mass height. So what do we do? Since they are the same, it means the average velocity. You got the same as the vx, is written as plus vs. Since initial velocity along s is written as vx. So just this times time. So the average speed, 2vs divided by 2 is vx times t. Now don't forget, the vx is written as a u word, ux. So what do we have? Distance along x-axis. So us is what? U cos t word. U cos theta, don't forget, times time. So it's time you're looking for. The Bible said by u cos theta. U cos theta. So what do we have? The time at x-axis, no, time for the time involved actually for the body to complete a movement along the x-axis, is simply this distance along the x-axis over u cos theta. Don't forget, this is not distance along y-axis, so it's not height. This is distance along the x-axis. Body covers distance along the x-axis, even though there's no acceleration along the x-axis. So we have our time already. So now we're going to put it into this. Let's use this next formula to get what we want. So this s equal to s equal to ut plus half at squared. So s equal to ut plus half at squared. Now all this is along the y-axis. What we have is along the y-axis. Don't forget the time is the time gotten from movement along the distance covered along the x-axis. Is the only time you can use for trajectory. You can't use the time for mass height because there's no restriction along mass height. The body, we're talking about position of a given body at any point in time. So mass height, there's a restriction, but for this one, there's no restriction. It could be at any point in time, and that's why we got the time for distance covered along x-axis. So it's going to come in handy for everything, both for y and x. So distance along y-axis is this, because the initial speed is u sine theta times time. What's the time? The time is distance along x-axis over u cos theta plus ut 1 over 2. Acceleration along y-axis, the body moved against gravity minus gravity times. So this acceleration along y-axis depends on a lot. It could be that the body is being shot down or the body is being thrown off. So it depends. It could be minus gravity, it could be plus gravity. A lot depends here. It could be plus gravity, it could be minus gravity, it depends. Then the time, what's the time? The time you're talking about here is this time, distance along x over u cos theta raised to power 2. That's what we have. So what do we have next? U cancels u. This this distance x sine theta divided by cos theta is tan theta. Tan theta, don't forget, sine is opposite over hypotenuse divided by cos adjacent over hypotenuse. Opposite over hypotenuse times hypotenuse over adjacent. When you invert them, we leave you with opposite over adjacent, which is tan theta. So this is it. This sy equal to s tan s. This one along s as tan theta, then plus then 1 over 2 times gravity, then times this distance along s as over u cos theta raised by 2. That's going to be distance along s as squared over u squared cos squared theta. So what do we have next? The next thing, we've gotten our formula already, but we could bring out the distance, because distance is here, distance is here. We could do that, or we could even leave it this way. We could leave it this way. So what's our final result? The final formula for projectile is distance along y-axis equal to distance tan theta plus, here it could be plus, here it could be negative, minus, depends on if the body is shot up or shot down. So it is g squared over 2u squared cos squared theta. So this is the formula for trajectory, as simple as that. Now, what trajectory does is that it shows the position of a given projectile at every given time instant. So, like the example we gave the other time, it could be there could be different scenarios that bring about trajectory. Somebody could be standing on a building, someone could be standing on a building, then project an object down from the building. Now, don't forget, this is going to be two things going to happen. The body will cover a distance along the y and also a distance along the s. The person could just throw it down like this, and even the person could project it at an angle like this. It could be a projection. Throw it up, so two things going to happen. The body covers a max height here, returns to this place, then keeps falling. So this one of the so when we talk about trajectory, we're talking about x distance along x and y axis at the same time. That's what trajectory is all about. So at the very point in time, we're drawing the curtain of today's lesson. Please, I would love you to go ahead and learn this formula. It's very important. Right from the next lesson, we start solving all kind of questions on that. So if you found this lesson, very lesson resourceful, please subscribe to the very channel at Edu Mosaic, and please give me a follow also on Facebook at Revelation Hub, and also share this lesson. See you in the next lesson. Thanks.